We're now going to begin our discussion of the one-step substitution reaction mechanism. So here's the overall reaction once again, but we talked about the fact that it's possible that the nucleophile could attack the electrophile and the leaving group leave at the same time. So in other words, bond breaking and bond formation occur simultaneously, and so this is what's called a concerted mechanism. If we look at the energy diagram for this reaction, you can see that it only consists of a single step, and I've labeled again the transition state, the activation energy, and then you have your reactants and products here that have a difference in enthalpy. Since this reaction only consists of one step, the rate law of the overall reaction is the rate law for that single step. Remember that when there's not an exponent shown here, that means it implies that the exponent is a 1. But what this is telling us is that the rate determining step depends on the collision of both of these species here. They're both involved. And so we add the exponents together to come up with a 2, and therefore we say that the rate law exhibits bimolecular kinetics. And therefore we call this reaction a nucleophilic substitution bimolecular, or an SN2 reaction. What we need to look at now is, what does the transition state of this single step look like? The transition state for the SN2 reaction looks something like this, where you have bond formation and bond breaking occurring at the same time. So we can think about factors that would stabilize this type of transition state and therefore lower the activation energy of the reaction and speed up the reaction. The big factor that comes into play with the SN2 reaction is that this transition state is rather crowded, and so it's very sensitive to steric strain.